Hi, I'm Benjamin Hunt, and I'm a biosystems engineering major, and I'm handling the mechanical and manufacturing process for this team.
My name is Jamie Holmstrom. I'm a chemical engineering major, and I'm the team lead on this project.
My name's Raina Kelly. I'm an engineering management major, and I'm the tech docs and system cohesion lead for this project.
My name is Gracie Reinholdt. I'm a biosystems engineer, and I'm the environmental risk mitigation lead.
My name is Daniel Hutton. I'm a chemical engineering major, and I'm the chemical engineering lead on this project.
I'm Celeste Cortez, and I'm an electrical and computer engineering major, and I am the procurement lead and also the electrical lead for this team.
Single-use plastic waste is a huge problem in today's society. It's of course a very easy thing to manufacture, but as far as the taking care of that waste is something that we are still struggling with, even in the United States. Only about 25% of plastic is recycled, as opposed to 75% being landfilled. This poses a significant problem in areas that don't have the space to landfill their plastic products. These island nations also can be easily cut off from fuel supplies during natural disasters. Both the plastic waste problem and the fuel problem can be solved through plastic pyrolysis.
The goal of this project was to design and build a portable plastic pyrolysis plant that could be transported around the world and deployed on island nations and areas that have been affected by natural disasters to turn plastic waste into an emergency fuel source.
Pyrolysis is simply the process of thermally decomposing carbon chains. If you think of a plastic molecule like a long chain of carbons, what pyrolysis does is snip those chains into shorter pieces. This transforms that solid plastic into a liquid oil. Ironically, this is the exact opposite process of making plastic, turning oil into plastic. This oil is similar in composition to diesel and can be used in its place. What we're doing is heating up the molecules to over 1,000 degrees Fahrenheit without any oxygen. Without oxygen, it can't combust, and therefore it just decomposes into a vapor. This vapor is then rapidly cooled in a condenser, and anything that condenses is now our pyrolysis oil. Anything that doesn't can be flared to stabilize any harmful pollutants.
This project requires that the system be compact and portable, weighing less than 1,000 pounds and being able to fit in the bed of a truck. This is to ensure that the system can be relocated to remote areas when needed. The system will generate oil on an order of 5 gallons of fuel per day, and the fuel will be similar in composition to liquid diesel. The system will have an intuitive design, which will make it operable by locals who are trained on site whenever it is needed. Finally, the most important safety features state that the system operates below 5 psi and that there are no open flames present within the system.
While health and safety standards for emergency disaster relief are often on a case-by-case basis, we are going to follow the National Emission Standards for Hazardous Pollutants published by the EPA. We would also like to consider the thresholds for the Hazard Risk Index and the Cancer Index, as well as indices for benzene, PCBs, and dioxins. These chemicals are pollutants that may be present in the flue gas produced by pyrolysis. These two analytical tools are used to measure and identify the chemicals present within the oil and gas samples that we will be collecting.
Pyrolysis is a relatively new field, and there's not a lot of published literature on the subject. By using a bench scale model before a full scale model, we're able to find the optimal parameters, including temperatures for the furnace and condenser, nitrogen flow rate, and others.
We also use this prototype to expedite our analysis testing time through using small batches of plastic. This prototype will be continually used to test parameters and optimize our full-scale design.
We determined that the optimal pyrolysis temperature is between 500 and 550 degrees Celsius. We also learned that a specific nitrogen flow rate is required to transport the pyrolysis products out of the system. The bench scale tests also helped us optimize our cooling water flow rate and cooling water temperature. Additionally, we optimized the heat exchange area necessary to maximize the liquid oil yield.
One of the important parts of both our bench scale and full scale design is being able to monitor some important parameters, such as the temperature in various locations, the pressure, and the oxygen within our system.
The first component of our bench scale pyrolysis plant is our nitrogen delivery system. So here we have our nitrogen tank and our nitrogen regulator and pressure gauge that helps us control the pressure that the nitrogen is delivered at. And these two flow meters help us control exactly how much nitrogen is flowed through these tubes. The nitrogen is delivered through the silicone hose and conveyed into our custom built quartz reaction vessel. This suspends the plastic sample inside of this tube furnace.
The temperature and heating rate of the furnace is controlled by a PID control room. Once the temperature has reached a high enough point to turn the plastic into a vapor, it will travel from the reaction vessel to the condenser. In the meantime, a pressure gauge monitors the pressure of the entire system, and if the pressure exceeds 5 psi, a pressure release valve will be released. Additionally, a thermocouple monitors the temperature of the gas before it reaches the condenser. The vapor travels through a condenser all the way down to a collection flask. The downstream temperature is monitored via another thermocouple, and the condenser is chilled via cooling water.
During normal operation, all non-condensable gas is sent through this tube and out through this bubbler into the fume hood. The bubbler is filled with water to prevent oxygen from backflowing into the tubes and creating a flammable hazard. When we want to sample the non-condensable gas, we use this three-way valve, simply open this port, and the gas flows through this tube and into this Tedlar sampling bag. When we're done filling the bag, we simply close this valve and the gas goes back through the bubbler. This valve is used to control the flow of the non-condensable gas into this oxygen meter, which tells us the percent by volume of oxygen in our system.
In case of emergencies, we have a sealed safety shield in place. Behind the shield, we have cameras monitoring the system pressure and the furnace temperature. In case of emergencies, we can use the emergency stop button to stop the heating of the system.
At the end of each experiment, we have samples of the liquid oil and the non-condensable gas, which we will test via gas chromatography and mass spectroscopy.
Oh hey, so you're checking out our full-scale plant. A little cooler than the bench scale, I might say. Let's take a closer look. Here, to start, we got our reaction vessel. This is 100 liters of stainless steel, and it will be where we heat up the plastic. We also have our pressure gauge here, and our insulation to protect the vessel.
As the plastic pyrolyzes, our vapors will escape through our gas outlet. First, we have our pressure relief valve. This is a safety feature to ensure no pressure buildup. We then have this long pipe that will lead to our condenser. This is where any of our heavier vapors can condense into our liquid output. As you can see, we have an inlet for the water and an outlet so that we are constantly having cool water transferred into our condenser bucket. Post-condenser, any liquids will travel down this pipe and be able to be released into our gas can and used as an energy source. Any uncondensable vapors will continue to our flare stack.
The non-condensable gases travel through here where they hit the molecular seal. This prevents a backflow of ambient air into the system. From there, the gases travel through the chimney where they hit the venturi burner. This flares the gases to stabilize any harmful byproducts.
Lastly, we have the 5 thermocouples that are connected to the full-scale design. The first one is the one that is touching the reactor to measure that temperature. We have the one at the top of the tank, which goes about 12 inches into the tank. We have one before the condenser to measure the temperature here, and one right after the condenser. Our last one can be seen under the table inside our cooling bucket, which will measure the temperature of our cooling water. And they're all connected to a breadboard and an Arduino Mega, and utilize MAX 6675 adapters to read all our thermocouple input.
The gas chromatography and mass spectroscopy analysis allowed us to identify the molecules in the oil and thus determine its quality as a fuel.
The oil we produced contains an abundance of the hydrocarbon nonene, which is commonly found in light diesel. The density of our oil is only 10% less than the density of light diesel, which indicates that it would make an appropriate substitute fuel in emergency situations.